Okay, so nav2. So we talked about ROS2 last week, and nav2 is kind of a big part in ROS2. Um, so what basically is like in when ROS1 was evolving like over this past decade, there was a lot of software that got added to the ROS framework, and a lot of details got cleared. Okay, the navigation system should have a controller, a planner, and all those different components. And when that thing got final, kind of crystallized, there was also this a navigation stack that got built in ROS1, but it was not super clear on like, okay, these are the different components. It's more like, okay, all these algorithms put together into one package, and it just worked out of the box, but you cannot modify a certain part of it. If you had to do it, it was much more harder. But now the nav stack on ROS1 was a big success. Like people could get a robot, they just install nav stack, and then if the robot is compatible, it'll just work fine out of the box. And so that kind of like motivated people to say that, okay, so navigation is kind of a critical piece. So they wanted to kind of upgrade that framework. So nav2 is kind of an upgrade for the nav stack that was in ROS1. Okay, so what it essentially has is it's basically a combination of algorithms, but essentially it is you have these containers where you can choose the algorithm that you want. So you have this framework where you have all these components stacked together. I'll show you the architecture in a bit, but you can swap between the different algorithms, whatever suits your robot and your sensors, and then use that out of the box. So that's kind of like the main thing with nav2. So it has things like path planning, obstacle avoidance, mapping, and localization. If you look at it, this is kind of like the main components of any navigation system. So you need to have some kind of sensing, and well, sensing is comes before that, but after that, after you have the sensing, you need to have some kind of mapping and localization. So you have to first localize, then you have to know how to build a map, and then you need to know like, okay, what are there in the map to avoid the obstacles, and then and then plan the path so that you can get around the obstacles. So it's kind of like an essential components of navigation system. So again, this ROS ROS2 nav2 was complete rewrite, as I said, because the previous nav stack was it's kind of a hodgepodge of like all the algorithms put together. So it was really hard to say like, okay, if you want to change an algorithm and use something else, it was not conducive for that. So they had to rewrite the whole thing. But what came out of that was like really useful. So this is kind of the high level architecture of the of ROS nav2. So if you look at it, there are multiple components to it. So let me just me go over one component at a time. So the first one is the planner. So a planner is basically like once you have the sensing data coming in, you need to figure out where do you want to get to, and once you figure out where you want to get to, you need to figure out which path you would take. And if you think about it in a simple sense, it's just, okay, just some points on the map. But then if you look at different scenarios, the planning itself gets a little complicated. So I'll talk about that in a bit. So you need to have like ways to incorporate multiple planners in your architecture. And then comes the controllers. So once you have the path, now you have to command your robot to travel through the path. So that's where the controllers come into play. So things like PID controllers and pure pursuit, these are kind of like the controllers that you can use. And then comes the smoothers. So when the planner is planning the path, it doesn't know of any kind of like, it generally doesn't know of the constraints of your robot. So it would have like these really sharp turns or jagged path. So there are two options there. One, you can include or incorporate your dynamics into your controller, and that would make it smoother, so that you won't end up having like really sharp turns. But a easier way, but less kind of like mathematical way, would be to just use a smoothing server where you just smooth the path so that you don't have these sharp turns anymore. So that's another approach, and the smoother server is something that does that. And then comes behavior. So this is something that was not there in ROS1 nav stack. This is it's kind of a culmination of all the different um, tools. I mean, I shouldn't call them tools. These are like different techniques that we'd use when the robot gets stuck. So for example, you got stuck and maybe you just have to turn in place to get unstuck, or you have to back up a certain distance to get unstuck. So depending on different robots have these different mechanisms, or these different tricks to get out of bad scenarios. And this behavior server is kind of like putting together all of those into one package where you can choose which one would work for your robot, and then use that instead of you going in and implementing the whole thing from scratch. So it's kind of like a new thing in ROS2. And then lifecycle management. So this is another new component in ROS2. So what this one does is it instead of okay, so every node or any process would have a life cycle. When I say life cycle, it's basically you start the node or the process, you allocate the memory, and you load the code, and then you run it. And in ROS1, it was not explicitly mentioned. So you do have this spin process that that you use to say whether your node is alive or not, and if it dies, then you check that and then you exit that. So it is kind of like implicit in ROS1. In ROS2, it was made explicit, where you have these different functions where you say that, okay, on startup do this, when you're on destroy do this, and when you're alive do this, and you can basically transition between these life cycles. So this is important basically when you have multiple nodes running together, and you depend on a feature on a different node for you to come up. So for example, let's say you have I mean, in a web application, let's say you have a UI that is populating data, and if you have a process that is talking to the database, you don't want the UI app to pull in the information before the database is initialized, right? Because if you pull in the data before the database is initialized, then you get nothing, and the UI is not populated with anything. So you need to make sure that the loading of the UI happens only after the database is connected and operational. So that's kind of like the thing that you want to do in with lifecycle management, and ROS2 explicitly provides that feature for your nav components. So just like that's kind of like a brief overview. So let me just go a little deeper again, not too deep. So this is so what is a planner, right? So the planner on a very high level is supposed to calculate the path from like when you from your start location to your end location. And it's kind of like I mean, that's kind of like a way, that's a simplistic thing to say. But then when you look into like, okay, how you do that, there are multiple factors that you need to consider. In addition to that, there are two types of planners. So people generally who are introduced to planner don't um, um, realize that there are two types. So that's why I wanted to kind of like mention that. So these are like global planner and local planner. So a global planner is something like you have the notion of a map. So you know where things are. Like if you already have a prior map, then you basically figure out, okay, from the start location to the end location, I know this is where the obstacles are. So let me just navigate. Let me just um, jot down the path for that. Um, to get to the destination. So a possible example is like, let's say you are on the moon, and then you have the map of the moon that the location that you landed, and so you would jot down the path from your current location to wherever location you want to get to. So that's kind of the global planning, and it could either happen on board on the robot or it could happen on ground. But then there is something called a local planner, and that takes care of the local information in the sense that whatever sensing data your robot gets, and then makes decision based off of that. So these are things that happen on board. This cannot happen off board. And so, for example, you have your global plan and you're trying to navigate to the location, but then you see that the sun is moving, so your shadows are changing. So you cannot drive in the dark. So you have to get in the region where it is where you still see the sun. So this you could pre-plan it in the global planner. Sometimes that happens, but most of the times it's happening in the local planner. Another possibility is like your global planner might not have the resolution, or the resolution of the map might not be that big. So for example, I think at this point we have like in certain regions we have resolution of like 1 meter per pixel. For a robot that is much smaller, that 1 meter is still like low resolution. So for the robot that we are building, it is we need like 10 centimeter per pixel. Like we don't like 1 centimeter, 1 meter per pixel is still like two cores resolution. So we cannot foresee or anticipate all the obstacles that the robot would encounter. So we have to do some kind of local planning to kind of avoid the obstacles that we didn't see in the global planner. So that's where the local planner would come in. So basically, it's like local planner is just looking at the local or like information that the robot sees in situ, like in from the sensor data, and then also the local planner is kind of like will not have the distance or the coverage that a global planner could have. So it's just limited to a particular distance with respect to the robot. And then the global planner is something that you assume that you know the map pretty much, and then you plan paths on that. So A star planner and all the variations of that falls under the global planner. So controllers, I said like controllers are commands I mean that basically translates a path to like commands to your robot or velocities that the robot would follow. So so you have a plan, and then you specify that, okay, let's say that you want to go straight here. So just like if it's a differential drive, you just give the same velocity for both the motors. And then when you want to turn here, then you would increase the left velocity and decrease the right velocity. So on a simplest sense, that's what a simple controller would do. But then if you have a really heavy robot, then the dynamics would come into play, where the robot would veer off, like it would not take this sharp turn. So in that case, the controller should kick in and say that, okay, let's drive a little bit more towards right, and then get into this path. So that's what a controller does. Like a path would just say that this is where you should go, and the controller would say like, okay, how do I make my robot go there? And then I talked about smoothers, right? So these are things that you would use to smooth the path based on like to kind of like help your robot or help your controller to be able to achieve that path. So there are simple smoothers like, well, I guess the simple smoother and the constraint smoother, where it's basically you add some mathematical constraints to the path so that you don't have these sharp turns and things like that. And then the behaviors. So I did mention, right, there are some behaviors in your robot where if you get stuck and you want to get unstuck, things like you just spin in place, or you just back up, or you just clear your map or clear your cost map. So things that I mean, when you look at it on a high level, this is like really simple things. Like, why do you want a component for that? But if you actually start building these robots and setting it up, you'll realize that you'll need these behaviors and you will end up implementing that. So it'll be better if someone has already thought about it and implemented, and you just have to you just get to use that. So for example, the clear cost map, this is one feature that we do use in our robot. I mean, so on the Luna robot that we have, there are times where the robot could get stuck. And when that happens, we would intentionally clear the map. And then when that happens, then the whole thing kind of um, uh, kicks in, like the process, all the process kicks in. So you get a new map, and then the robot would continue driving. So so these are kind of things that you would generally use in a robot. And once you start using setting up robots to do these things, then you will figure out that, okay, these are useful features. So that's what this does. And then finally, we have the life cycle management, where, as I said, like you define what happens when you create the app versus when you shut down the app, and then like what are the things you would do to configure. So there are these different states, right? So it's in the unconfigured state to inactive state, and then the active state, and then after that, it's in the, like after unconfigured, I think it can get to the finalized state when before you are ready to destroy or kill the app. So it's kind of like detailed lifecycle management, and I already mentioned like why we need that. So so that's what ROS provides. So it's kind of made more explicit so that you can control this, or uh, kind of like have this as checkpoints to say that which state each app has to be in a particular time frame, and it gives you that control. So that's pretty much on nav2. Again, we could have like a whole kind of a course on nav2 because it's pretty detailed, but this is kind of an overview for people who are just getting started with ROS or ROS2 and trying to see like where things are. Um, so so that's kind of what that covers the nav2 part. And I mean, so this, as I said, this is a lecture I was giving in at CMU. So I was also showing them some of the demo. I don't know if that's useful here, but let me just say something basics about ROS itself. Like when you're working with ROS, these are the three main ways in which the nodes are communicating between each other. So the first mode is publish subscriber mode, where each node would publish a message, or like whichever node wants to publish something, it will publish a message, and then a node that wants to listen to it just subscribes to that topic, and then it just gets that information. So that's kind of like the basic mode of operation. The second mode, a little bit more complicated, is you have something called services. So what you do here is, in the message or the publish subscribe model, you don't have, or like if you're saying that, okay, I want to do certain things, so node A says node B to do something. If it's instantaneous, then it will do it, and then it will publish the result. But there are things where it is not instantaneous, right? So some requests like, okay, compute this checksum, or maybe compute this um, um, like error in this, or detect the object in this image. Those kind of operations are not instantaneous. So for those things, you use something called a service architecture, where you have a service or a server, and your node would say that, okay, I want this operation, and then the node that is doing the service would perform that operation, and then after a while, once it's done, it can say that, okay, I'm done, this is the response, or it can say that, okay, I failed, and this is the response. So for operations that are a little bit longer running, you use the service architecture. And then there is something else called action clients. So these are things where if you have services that are running much longer. So for example, in the previous example, in the previous setup, if you have a service that is running, let's say for 10 seconds, you can have a service architecture. But then if you have an operation that is running for, let's say, 10 minutes, then you cannot just wait 10 minutes to see like if that app is if the operation is still running or if it crashed, like that would be too long to wait. So then you use something called an action service or action server client architecture, where you can send intermediate results. So you send a goal, and then the node that is doing it would start doing the operation, but um, it would keep sending responses saying that, okay, I'm 10% done, or I'm halfway through. You can send whatever response you want to for the client who's receiving to see that, oh, okay, this operation is still being performed, nothing crashed, nothing failed. So you can wait for that time, and then finally, when it's done, the action server would say that, okay, I'm done. So for long running operations, you'd use an architecture like this. So these are the three major architectures for communication between the nodes, and that's all you need to know to actually use these, like set up different nodes and talk between them. And it, the you would use the publish service thing, subscribe thing, pretty much for most of the nodes. Services is some we use that sometimes, but action service is something that we rarely use. But it's good to know that these things exist. So I think that's about it. I think I can show a demo, which is basically like starting the talker node and listener node, and showing the publisher subscriber thing. If there is interest there, I can do that. Um, but that's pretty much it. So let me know if you guys want me to show you like a simple raw setup. And also questions, like if you have questions from whatever I was talking about, feel free to ask.
Sure. What if there are two subscribers for a single topic? Uh,
Mhm. Yeah.
Sorry, there are two publishers for a single topic and one subscriber. Then there
Okay.
might be a discrepancy with the published idea, right? Like there might be two commands for subscriber. Then how will it choose?
It will not. So that's the thing, right? So if you have two publishers, which is generally a bad idea to do it, but if you have that, the subscriber will not be able to distinguish between, well, you can add something there to distinguish it, but it will not be able to. So so let me see, hold on. Let me draw something. Okay, so let's say publisher one. Let me give you an example. So this is navigator. Okay. Um, so we have something like this, and let's say this is the message bus. Sorry. Oh my God. I'm messing up the image. Anyway, so okay, so these are so this is a message bus, and there are two publishers and one subscriber. So in this case, it's a real scenario where we are sending drive commands from the navigator, but we can also joystick the robot. So we'll send drive commands from the joystick as well. And this is a subscriber. The subscriber, he doesn't care where that the drive commands are coming from, as long as it's the same message. So the subscriber can listen to both the messages and it will just operate fine. But you have to make sure that the navigator and the joystick are not talking at the same time, because that will be conflicting commands, right? So kind of like a practical scenario here is, so we have so on Zoe 1, I mean, the Zoe robot, I don't know if you guys are familiar with that. Um, so we have a navigator in there, and then we would just let the navigator drive the robot. And this is like driving in the desert. So there are times where you have to be careful, and if the navigator does something stupid, you want to stop the robot before it falls into a ditch or like a cliff. So we'll basically walk behind the robot or like drive behind the robot. So we'll have the joystick ready if something bad happens. And when that is happening, you want to switch to the joystick when the navigator is doing something stupid. So the way we have set it up is like when the joystick turns on, the navigator looks for that signal and then it will stop sending commands. It will stop sending drive commands because the subscriber will not know that, will not know whether it's coming from the navigator or the joystick. So that basically just listens to the messages and acts accordingly. So that's the way we implemented it. You could also make the subscriber do the thing, like in the sense that you can add a field in the message saying that who is sending it, either the navigator or the joystick. And then in the subscriber, you can say that, okay, if it's a joystick, then don't listen to the navigator message, just skip it. So that's doable, but we chose to implement it on the publishers. So again, there has to be extra logic defined somewhere to kind of make sure that there are no conflicts. So that falls on you. There is nothing that the framework itself, ROS, doesn't give you anything to kind of resolve that, because I mean, the framework would not know what to do, right? Is that clear?
Yes, sir.
Okay. Okay. So any other questions? So do you need me to, do you think it'll be useful for me to just fire up a ROS thing? Like, how familiar are you guys with ROS setup? Have you tried ROS before?
Yes, I've actually tried it.
Tried it. Okay, so then the simple demo is not going to be helpful there.
I've
Shifting.
never worked with it, so I'm interested in seeing that if
Okay.
there is time.
Yeah, sure. Yeah. So, okay. So I will set it up. Hold on. Let me fire up my VM. Yeah, just give me a second. I'm just turning on my VM. Okay, let me share my screen. Okay, do you see my screen?
Yeah, it's there.
Okay, cool. Okay, so again, this is a multi-node architecture, right? So let's just have two screens. So there are these demo kind of like processes that, like, when once you install ROS2, you can just use these to test or kind of like understand how ROS works in the background. So let me start one of those demo nodes. So this is called um, demo nodes. I think they have both in C++ and Python. So, okay, I'm starting a demo node. It's called Talker. What it does is it's just publishing a message like hello world and then number. So it's just like publishing the thing. So there are ROS commands that would let you look at the nodes that are running. So let's start with that. So ROS2 node list. So this should show you the list of nodes that are running. So right now it's just the talker. This is a node that's running. And then we can also look at the topics that are being published. So right now the Docker node is publishing the message to this topic chatter. So we can use another ROS command called ROS2 topic echo and to look at the messages that are being published. So when I do the echo, then you see that this message that is being published by the talker, you get that. So this is actually the message that is being published. So you get that. Okay. So next, let's start the listener node. That's another demo node. So this is ROS2 demo nodes. Okay. So the listener node, it basically listens to the talker node and shows you the message that is being published. So in this case, it's basically shows the message that you receive. So that's that. So let's split the screen. So it's basically like the message passing system that we talked about, right? So one node sending the message, the other node kind of listening that. There is also a different kind of like, I think, let me see. Okay. Is it RTD graph? Yeah. So there is a program called RQT graph that would show you all the nodes and the messages and the listener node. So in this case, we have the talker, which is sending the messages. And then we have the listener that is listening to the message. And then chatter is the message that is being published. So there are tools like this, which helps you to kind of like listen to the system and see what happens in the background. So for this simple scenario, this is kind of an overkill, like just having showing the processes and the messages. But then if you have a really complex system where you have like tons of these processes running and a lot of messages going across, then this would be like really useful, because then you know like what are all the topics, what are the messages, how they are connected. You can follow the graph and everything. So that's where it'll be useful. So let's also can I just do another listener? Okay, so in this case, I started another listener. It's going to be, so again, this is kind of like the magic with ROS. The publisher doesn't need to know there is another listener. You just start another one, and then it's getting the same message that the publisher is publishing. Now, if you start RQT graph, let's see what it shows. Oh, it just shows the same one. It should actually show two nodes.
You should actually rename it. Otherwise, it will be taking
Oh,
it as space.
is it taking the same name? Oh God, okay. I don't remember the syntax for
It's something like map is there, if I'm right.
map.
I'm not sure.
Yeah, I mean, I don't remember the syntax. Anyway, so one other thing, okay, let me just pull that up. Okay. Let me look up the syntax for that. Just start a simple one. Okay, underscore node. Maybe this will work. I actually wanted to do a publisher. I don't know if this will work, but let's see. Okay, so now let's there you go. Okay, so this is actually going into the scenario that Krishna was mentioning. So if you can see here, there are two talkers, talker 1 and talker 2. and then both of them are publishing the same message, and the listener is listening to it. So if you look at it, Talker 1 has been publishing, and it's like around 300 and something. And then the Talker 2 is publishing, it's around the 30 something. And then if you look at the listener, you can see that it's getting both the messages intermittently. So that's kind of like the what will happen if you have two publishers publishing the same message at the same time. And as you can see, we have these two different nodes. So now I think it's getting a little kind of clear. Okay, we have two nodes talking to the same message, publishing the same message, and then we have one listener. So that's kind of what these tools are. You can also look at this from a command line. So if you do ROS topic list, we get the messages, and then if you use info, that's the thing. So then we look at the topic. So we wanted to look at the node info, right? So ROS topic. Node list. Let's look at the list of nodes. We have Talker and Talker 1, Talker 2, node info. Okay, so again, these are commands that pretty useful commands. Once you get used to it, it can like acts as second nature. You just look through it and kind of debug the system. So what this one does is the topic command basically lets you inspect the topic. So the list command would tell you like what are the topics. The info command would say like what that topic is. So in this case, it's basically a string, and you have two publishers and one subscriber. And then the node command would give you the number of nodes that are running. So in this case, there are 3 nodes running. And then the info command on that would tell you what that particular node is doing. So in this case, the listener has a subscriber. It's called it's subscribing to the chatter messages, and then the parameter events. This is kind of default ROS2 stuff, so you don't have to worry about that. And then you have the publishers. It is not right now, it is not actively publishing anything, so that's you don't have anything for that. And then services call, so these are all like the ROS2 services that it's listening to, so don't have to worry about it. And then the action servers and clients that I talked about. So basically you can kind of inspect the system in the command line. This is what you would generally do, but you want to do, if you want to get a big picture view, then you would use the RQT graph command to get this whole graph information. So maybe I'll also show you the services thing that I talked about. So let's see. Why is my okay? So there is another demo node for that. So this one it just adds 2 integers. So it's called add to int server. So the server is running here, and then let's start a listener or the client that calls the service. So roster service call add to ints. So basically here I'm telling what are the numbers. So this is the message format. So I'm basically following that format and giving 2 numbers. And so if you look at it, it's saying that waiting for service. I mean, adding 2 numbers is kind of instantaneous, but essentially what it does is it talks to the service, and the service kind of does the calculation. So it did the calculation, and then you got a response, and it says it's fine. So obviously you will not use it for a simple thing like this, but for complex learning operations, you can use the service. So that's how a service kind of operates. There are a bunch of other things like I was showing the students like like the RBus interface, the things about ROS-bag and simulation and everything. So maybe I'll just briefly mention about ROS-bag here. So let's just run the Docker again, and then let's do record a ROS-bag. So I'll mention what ROS-bag is in a bit. Oh, is it ROS2 bag, right? Okay. So I recorded something. So what I did was I started a publisher, which is just Docker, publishing this data. And then what I did was I went in and said that I want to record that data, record that information. So I kind of like called a program called bag. So bag is like, you can think of it as like a bag where you store the data. And -a is basically recording all the topics here. And what it did was it recorded the data. So where did it put it? It should have, okay, yeah, it's put it here. Okay, so this is where the data was captured. So you can actually play back. Okay, this is also published. Let's get that. Raster bag. Play. Okay, so let's do topic list. So if you look at lost to topic list, you see that nothing like there is no chatter message here, right? But then when I start playing the bag, and when you do that, you would see that the chatter message is being published now. So there is no publisher running, but the bag file, or basically the one which recorded it, would play back the data at the same rate as it was as it received it. So we can also do ROS to topic echo / chatter. So it's not published, but let's do the bag file and then do the publishing. Then you see that messages that are coming through, and then the bag stops, the publishing kind of stops. So, I mean, again, this is on a very high level. Sure, just getting started. This looks like, oh yeah, okay, that's great. So what? That's the kind of question you would have. But if you are in the field recording data, like if you're in the field like generating data from the robot, and you want to record the data in the past, like before ROS ecosystem was there, everyone had their own custom way of recording the data, and then playing back the data is kind of like a big problem by itself, right? You need to make sure that the timing is all correct, because all the algorithms would depend on that. And if you get this timing off, then your algorithms would not behave the same way when you're deploying it back on the robot. So there was this need for reproducing the data the same way it was generated by the robot. And I was working on a framework called NV at that time, and they had this whole like complex architecture to kind of record the data and replay it at the same time, and it still was buggy. And ROS kind of like saved the day because they had this whole thing set up, and an easy way to kind of like record and play back. ROS2 kind of like improved on that, and so they're now using different formats and things like that. But essentially, it's just a very useful feature once you start working with real robots. Because what generally happens is collect the robot in you collect the data in the field, you go back and then you work on the algorithm using that data that you collected. You just keep playing it back and working on the algorithm. And once you're satisfied, then you go back to the field and test it out. That's generally how things happen. So you need features like this to make that happen. Okay, so that's kind of the demo and a little bit about ROS2. Questions? Okay.
Like I've got the stuff. I'm
Okay.
audible.
Yeah.
It's like how do we actually fine tune these publishing and subscription rates in the real robots? If I know I've heard about this because different sensors have different like rate at which they actually measure state data. So we actually manually tune those, or we have some helper tools or softwares like that.
So the in ROS 1, this was not even possible. Okay, so that's where I'll start. So ROS 1, there is no way of setting the data rate on these. So basically, if you look at it, it's all pipes, right? So you have this message bus, and each node is having a pipe. And what you're asking is like, how can we specify how wide the pipe is so that we have data coming through, or how narrow the pipe is if it's a low processing unit, right? So in ROS1, there was no way of controlling that these pipes. So whatever rate things gets published would go to the subscriber, even if the subscriber is a low power device. In ROS2, there is the DDS layer, the middleware layer that I was talking about, that actually provides that functionality. So you could specify the throughput. You could specify like how big the pipe has to be. You could also specify that okay, this is a low end device, so I don't need, I only can take in this much of data rate. So you could actually specify that in that middleware layer. So ROS exposes that info that kind of functionality, so you can configure that. So, but it also depends on how well that uh, functionality is implemented in the middleware, right? Because ROS itself does not do that. It is the middleware that is implementing it. So as I said last week, there are multiple vendors for these middleware. And there are free ones that ROS2 uses, but then there are also paid ones that in this defense industry and other people use, where they can fine tune this thing um, to their needs. So that's where the middleware kind of like, okay, what middleware would you use, and like why would you use that because of all these features.
I've got this one related question. Like,
Mhm.
is this where the exactly where we use the quality of service thing?
Sorry,
Is it some kind of related to the quality of service, like
it is quality
QoS?
of service. Yeah, yeah. It is a
Okay,
QoS thing. Yeah, yeah,
got it.
yeah. Yeah. So yeah, I mean, so for most of the robot applications, you generally wouldn't use, you don't have to, because I mean, ROS1 was there for a decade, and there was no quality of service there. But for some applications, you do need, and when you need that, and if you don't have that, it'll be a pain, right? Um, so that's what ROS2 provides. But for most of your applications, if you're just doing it on your computer, or even on the robot which have like a general purpose computer, you don't have to deal with it. It becomes a problem when you have these embedded systems, or you have systems which have very limited connectivity. Then you talk about those features. So personally, I haven't used those QoS features um, on my robots, because like most of them do have the bandwidth and everything. But I have friends who have used it, and for scenarios where like there was this challenge called Sapti challenge, where they're developing multiple robots going into underground caves and mapping them. So in those projects, there were multiple robots, like a drone and a ground robot and like a walking quadruped, and everything kind of like talking together. And in this case, like the drone might not have the bandwidth, or might be too far away from the ground robot. So you have to make sure that you have the parameters set correctly so that you get the essential information, but not all of them. So so those are the scenarios you would generally set it. Um, and again, in a multi-robot setup, I generally don't work with multi-robot setup, so I haven't personally used that.
Okay, cool.
Okay. Mhm. Any questions? Okay, looks like my internet connection is unstable. Okay, so there are no other questions. I think we can wrap it up. Thanks for joining, guys. I'll see you next week.
Bye.
Bye, guys. Thank you.
Bye. See you.